Section 10.4, Fibonacci numbers and the golden ratio. Goals here, we want to find Fibonacci numbers, which we'll talk about what they are here very shortly. And then we want to understand the relationship between Fibonacci numbers and this thing called the golden ratio. And again, we'll see what that is as we get there. Basically, in this section, we're going to explore an interesting sequence of numbers, Fibonacci numbers, that has relationships to art, nature, and science. And it's crazy how much they show up in nature and just in general. And that's why mathematicians geek out over them so much. That's why they're, in this section. They got their own section in a book, and they often do. So it's crazy when people started seeing where these numbers were showing up. They're like, oh, it's a Fibonacci number. Oh, it's another Fibonacci number. It's just mind-blowing how many places they show up. But the sequence was first mentioned in Western mathematics by Leonardo Pisano as an exploration about a population of rabbits. So the idea is that right here, you're starting with one pair, and we're going to assume this pair of rabbits, they can't breed yet. So in the first cycle or whatever, there's just one pair of rabbits. Then they mature. So they've matured now. They can have an offspring, they can produce offspring, and in the next cycle they do. So they produce an offspring that pairs up with another one, and then they're still living. So we start out with one immature pair, they matured, still had one pair, and now there's going to be two pairs, that original pair and then their offspring paired up with another. Then we come down a line, and the old pair still there. They were able to have another offspring that paired up, so over here. And then the original offspring, this one right here, that paired up, they weren't able to have children yet, so they just keep coming down. But now we've gone from 1 to 1 to 2 to 3, and then moving to the last one here, the original pair continues. The pair that they had, or the one they had that paired up with another, didn't produce yet, but now they've matured here. The original pair, they produced another offspring that paired up with somebody else, and then this, their original offspring that paired up, they finally matured, they keep going, and then they produce an offspring that pairs up with somebody else. So now they've gone from 1 to 1 to 2 to 3 to 5. And one thing to note here, and this is what makes the Fibonacci sequence Fibonacci, is that if you take the first two pair amounts, 1 plus 1, you get 2 down there. If you add 1 and 2, you get 3. If you add 2 and 3, you get 5. And this recursively defined sequence, where you add the two prior numbers to get the next one, this is the nature of Fibonacci. So the sequence is defined recursively, and this means that each term is defined by the previous term or terms. There are many recursive sequences out there in mathematics. Fibonacci is just one of them, and it uses the two prior terms. So basically, in math definition, the Fibonacci sequence is defined by f sub n, so the nth Fibonacci number is equal to the f of the n minus 1, so the term right before it, added to the term with the n minus 2, which means two terms before it, for all n greater than or equal to 3. So it only starts, the f sub n with this formula only starts at 3 because they kind of have to seed the recursive sequence with two prior terms to begin with. If you don't know two prior terms or the first two terms, you can't start things. So they always, with these recursives, they'll give you a seed, so to speak, to start things. And here we needed 2 seeds because we had 2 prior terms being added together. So they'll say, okay, f sub 1 is 1, f sub 2 is 2, or is 1, sorry. And then for 3, you would just add f sub 1 and f sub 2. And that's why they start it at 3. And then you just keep going. So up here, what we have, just kind of putting some notation to these different ones, this would be f sub 1 plus f sub 2 equals f sub 3. This is really f sub 2 plus f sub 3 equaling f sub 4. And then this one was f sub 3 plus f sub 4, giving you f sub 5. And that's basically how the Fibonacci sequence works. So when you're working with these in the homework, you're going to be doing things either based with that formula, or maybe they'll give you something like this, where it's like, okay, here's f sub 5 is 5, f sub 6 is 8, find f sub 7, and we're going to go ahead and find f sub 4, which might be a little crazy, but we're going to do it. So I want you to think about that for a second. Okay, hopefully you did. And let's see how this works. So let's start out with f sub 7. This one's the easy one. It's just going to be the f sub 7 minus 1 plus the f sub 7 minus 2, using that formula that defines the Fibonacci sequence. Well, this really is just f sub 6 plus f sub 5. And that means that we're just going to add 8 and 5 together, and we get 13. So that's all you really got to do. You just got to trust the formula, so to speak. Now, f sub 4 is a little different to get to. So the way we need to think about this, I have f sub 6, I have f sub 5, I need f sub 4. And what you have to realize is that f sub 6 was equal to f5 plus the f4. The 2 prior terms add together to give you the next one. So to get 6, we needed 5 and 4. And I know 6 is 8. I know 5 was 5. So I can use this to solve for f sub 4, subtract 5 from both sides, and you get that 3 was f sub 4. So you might be asked to do something like that, just a different use of the formula as you go through the homework. All right, so this sequence, the formula, works out great, but the recursive process can be tedious if you want higher index numbers, things like f sub 30. Then you just got to keep going, find 29 and 28, which means you got to go back 20. You just got to keep working your way back. And basically, you start at the 1 and the 2, and you get to the 3, then the 4, then the 5, and you go all the way up to 30. Imagine if you want f sub 100. And mathematicians, being efficiency-minded, they wanted to find a better way. So people often look for explicit formulas that do not rely on recursion. And it isn't always possible, but sometimes it is. And the Fibonacci's do have an explicit formula that was rediscovered by Jacques Binet after it was lost for 100 years. Leonhard Euler is said to have first derived it. So Euler's number, that E that equals 2.718 that you worked with before, the same person. And if memory serves, he was a lawyer by trade. And back in his day, you didn't come home and just turn on the radio or turn on the internet or TV streaming, whatever you do, your video games. There wasn't nearly the amount of distraction back in those days. You basically had the fire. that was what you had to stare at. So Leonhard Euler, would be a lawyer in day, and then in his spare time he worked on math. And you'll see he's got stuff all over the place in mathematics, random places, because he wasn't like a specialist in a certain field. He just enjoyed the world of math, and he would get caught on something and run with it. So anyway, You'll probably see his name in other places if you were to go on in math. But we're going to use Benet's simplified formula in this class. And the simplified formula, you can find the nth Fibonacci number by using this following formula. And these double brackets here, if you're wondering what those are, it just means you round to the nearest integer. So that's all that means, because you're not going to get a whole number necessarily out of this. But you take 1 plus the square root of 5 over 2, you raise that to the nth power, whatever the number you're looking for, power, and then you divide that result by the square root of 5, and then you round to the nearest integer. So let's see an example of this. And we're going to look at f sub 25. So we're going to have our double bracket here with the round to the nearest integer implication. We're going to take this 1 plus square root of 5 over 2 raised to the 25th power, divide that result by the square root of 5, and then that will give us something that we can round to the nearest integer to get the Fibonacci number. When you figure out the stuff in the parentheses, putting that in your calculator or in the Desmos or something, you'll get 75,024.99. Rounding to the nearest integer, you get 75,025. And that is, if you were to check this using recursion, that is the 25th Fibonacci number, obtained by adding the 24th and the 23rd, obtained by blah, 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 all the way back down. So it's pretty cool that you don't have to use recursion to get there. You just have to plug the desired term into this formula, and it'll give you the result at the end. All right, I'm going to go ahead and stop there because I don't have a lot left, but it's more than 3 minutes, and I want to show you some things about the golden ratio here shortly. So I will pick up in part 2.